Hey everyone, and welcome back to The Explainer. Today we're going to embark on a truly fascinating journey. We are going to completely demystify a mathematical concept that honestly sounds incredibly intimidating, but is actually one of the most beautiful, elegant, and useful shortcuts in all of algebra. I'm talking about the binomial theorem. Now, if you've ever looked at a massive algebraic equation and just felt a wave of panic, don't worry. By the end of this explainer, you're going to see the hidden patterns that make solving those big problems an absolute breeze. We're taking a trip from the brilliant geometry of Pascal all the way to the absolute genius of Isaac Newton.
Okay, let's dive right in. Here is our roadmap for today. We'll start with the expansion problem, then look at Pascal's magical triangle, uncover the secret of combinatorics, explore Newton's infinite generalization, look at some real-world applications, and finish up with a final knowledge check.
Section 1. The expansion problem, or why multiplying is just so incredibly tedious. You know, every great mathematical tool starts with a problem that someone was just, too frustrated to keep doing the hard way. That's our mathematical heroes problem for today. Imagine you're given this challenge. How do you multiply the expression a plus b by itself 10 times without literally losing your mind? You know, a plus b times a plus b times a plus b, 10 whole times. If you tried to do this manually and multiplying every single term by every other term, you'd end up with a sprawling, chaotic mess of variables.
Think about it, expanding a plus b squared. That's a piece of cake. It gives us a simple three-term expression, a squared plus 2ab plus b squared. Most of us just memorized that back in high school. But expanding a plus b to the power of 10, that is an absolute nightmare to calculate manually term by term. The expansion becomes so lengthy and so tedious that the risk of making a basic, silly arithmetic mistake basically approaches 100%. We need a shortcut.
But hey, real quick, before we get to that magic shortcut, let's just make sure we have our foundational definitions locked in. What exactly is a binomial? Very simply, it's an algebraic expression that contains exactly two dissimilar terms. Just think of the prefix bi, meaning two, like a bicycle. So x plus y, that's a binomial, or a minus b. It's the core building block of those massive equations we want to solve. Moving on to Section 2, Pascal's magical triangle, basically the mathematical cheat code. So, the French mathematician Blaise Pascal popularized this incredibly simple geometric arrangement of numbers that turns out to be a magic key for algebra. Here's how you build it. Step 1, you just start with ones on the outside borders creating a triangle shape. Then step 2, to find any number inside the triangle, you simply add the two numbers directly above it. So 1 plus 1 gives you 2, 1 plus 2 gives you 3. And this brilliantly illustrates how incredibly complex math can emerge from the absolute simplest, most repetitive arithmetic rules. Okay, so why on earth do we care about adding numbers in a triangle? Well, the rows of Pascal's triangle correspond perfectly to the coefficients of our expanded binomial terms. If you're raising a binomial to the power of 2, our simple a plus b squared, you just look at row 2. The numbers are 1, 2, 1. And what were the coefficients of a squared plus 2ab plus b squared? 1, 2, 1. If you want to raise it to the power of 4, you don't have to multiply everything out. You just look down at the fourth row. 1, 4, 6, 4, 1. Those are your multipliers. It is almost shockingly elegant, right?
Section 3. The secret of combinatorics. Let's look under the mathematical hood. You see, Pascal's triangle isn't just some neat magic trick. It's deeply rooted in the fine art of counting. The numbers in it actually represent combinations, specifically a mathematical concept we call n choose k. Basically, this means calculating how many ways you can choose a subset of k elements from a total set of n elements. And these aren't just abstract floating numbers. They apply to the real world. For example, if you flip a coin n times, how many different ways can you get exactly k heads? Or think of block walking on a city grid. How many direct routes are there if you have to make exactly k turns? The answers to those real-world questions are the exact same numbers sitting inside Pascal's triangle.
So, the really crucial point here is how all of these seemingly different concepts perfectly align, whether we're calculating the strict algebraic formula of 2 choose 1, or we're figuring out how to get one head from 2 coin flips, or finding a route with one turn over 2 city blocks, the answer is always 2. And right there, sitting dead center in row 2 of Pascal's triangle, is that exact same number. The binomial theorem is really just a clever way of counting how many ways terms can combine when you multiply them together.
All right, Section 4, Newton's infinite generalization. Time to break some mathematical rules. Now, this is where our story takes a fun historical plot twist. Enter Isaac Newton in the 17th century. He enrolls at Cambridge University in 1661, completely immersing himself in the works of Galileo and Descartes. By 1665, while he's trying to solve these incredibly complex physics problems involving motion and calculating tangents for his brand new invention, which we now call calculus, he realizes Pascal's triangle has a hard limit. He needs a better tool. So, he just invents the generalized binomial theorem. But in true classic Newton fashion, he doesn't even bother publishing it right away. It actually took until 1711, after being heavily pushed by fellow mathematician Abraham de Moivre, for it to finally see the light of day.
So why was Newton's version such a massive, game-changing leap? Well, the standard theorem, using Pascal's triangle, only works if your exponent is a whole positive integer, like 2 or 4 or 10, and the sequence eventually ends, right? It has a finite number of terms. But Newton's generalization literally blew the doors off this limitation. He proved that you could use fractional exponents, and even negative numbers. The catch? Well, for fractions and negatives, the expansion never actually stops. It continues forever as an infinite series. This was a groundbreaking leap that quite literally made the invention of modern calculus possible.
Section 5. Real-world applications. Let's see why this actually matters today.
Let's move on and see how this builds into stuff we actually use right now. Because Newton's breakthrough wasn't just theoretical. Today, the binomial theorem is a heavy lifter across all the sciences. It allows computers to approximate the square root of massive, highly complex numbers using just basic arithmetic. It is the absolute foundation of deriving power series in calculus. Over in manufacturing, it's used to simplify probability models to predict product faults over millions of trials. And it paved the way for the analytical methods that engineers and physicists rely on every single day to model our physical world.
Now, what's really interesting here is how all of this comes together into one unified cheat sheet. You can see exactly how the combinatorial formulas and Pascal's triangle weave together to expand these large powers. It takes an impossible manual calculation and turns it into a simple plug-and-play formula. It's literally the ultimate time saver.
And finally, Section 6, our final knowledge check. Let's test your understanding. All right, it's time for a quick, rapid-fire quiz to really cement these concepts in your brain. Question 1. If you are expanding the binomial x plus y all to the power of 10, what is the total number of terms in the final expanded expression? Think back to our early examples for a second. Did you guess 11? Because the answer is 11. Remember the really simple rule, the total number of terms is always n plus 1. So a power of 10 gives us 11 terms.
Okay, question 2. Let's test your visual memory of Pascal's triangle. What is the third coefficient in the expansion of power 4? Remember the row starts with 1, then 4. What comes next right in the middle?
The answer is 6. The sequence for power 4 goes 1, 4, 6, 4, 1. The pure symmetry of the triangle is what makes it so beautiful and easy to remember.
Last one, question 3. A little history and theory for you. True or false? If you use Newton's generalization to find a square root, which remember is a fractional power of 1/2, the series will eventually end. Think about what Newton fundamentally changed.